Cambridge International AS and A-Levels Chemistry, Paper 2 AS Level Structured Questions, October-November 2025, Paper 24. Group 17 elements are oxidizing agents. Explain how group 17 elements can act as oxidizing agents. So what do you mean by an oxidizing agent? If one substance oxidizes another, what does it mean? It means it's taking out electrons, because we know that oxidizing means to take out electrons, and oxidation is the loss of electrons. So oxidizing means to take out electrons. So if they're saying that something's being an oxidizing agent, it means it's taking out electrons of something. And we know group 17 elements like the fluorine, chlorine, bromine, what do these guys do? They're in group 17. They need just one more electron to stabilize themselves. If they just need one more electron, what are they going to do? They're going to be hungry, they're going to be greedy for that one electron, and the hunger and greed for that electron is going to make them like the stronger oxidizing agent. They're going to take out electrons in seconds and minutes, in nanoseconds, from other atoms, like very quickly, because they're hungry for electrons. That's why they can act as oxidizing agents. So we're going to write that it's simple. They just need one more to stabilize themselves. Like if they need two more, it might make them weaker, like oxidizing agent. But one means it's gonna happen damn quick. So they can take out electrons from other atoms. Or you can write in a different way. They can make other atoms lose electrons. It's the same thing. It's just telling they're good oxidizing agents. Write an equation to show the reaction of Cl2 oxidizes aluminum metal. Now look, what's happening is chlorine is oxidizing aluminum. Do you understand the dynamics of the question? What's happening over here is that you have aluminum. Aluminum wants to lose electrons. Aluminum is in group 13. It has 3 electrons, let me just draw it properly so you guys understand what kind of stuff is going on. So this is aluminum, first shell, second shell, third shell. In the third shell, aluminum has 1, 2, and 3 electrons, and aluminum wants to get rid of these 3 electrons. I know this is elementary school science, I know that's basic, but the basics is what they're asking in your A-levels question. You just got to be clear with the basics, that what's happening, you got to be clear with it. Aluminum wants to lose these 3 electrons. And chlorine is a dash thing waiting to take away someone's electrons. Chlorine has 7 electrons in its outer shell. 1, 2, 3, 4, 5, 6, 7, right? So aluminum is ready to give 3 electrons and chlorine is ready to gain electrons. So what's going to happen is this 1 electron from here is going to shift from here to chlorine. Got it? So that's how chlorine is going to oxidize aluminum. It's going to make it lose its electrons. And aluminum is willing to lose the electrons. Got it? So over here, what we're going to write? We have to write an equation of simple reaction. Ionic bond formation between aluminum and chlorine. Okay, there's no rocket science in it. The way the examiner is phrased the question is a bit like interesting. How does chlorine oxidize aluminum? If he asks how does aluminum reduces chlorine, so that's like a bit of a trick. But the thing over here you got to realize is that you have 1 aluminum, you have Cl2, and then what do you form? You form AlCl3 because you know chlorine and aluminum. So AlCl3 because aluminum is going to lose 3 electrons. It's going to get a 3 plus charge. And chlorine is going to gain 1 electron. So it's going to get a negative 1 charge. So you got to balance it out. Simple. How do we balance it out? We put a 2 over here. We put a 3 over here. And then we put a 2 over here. Balanced? Good. A student heats equal amounts of iodine and hydrogen in a sealed flask. The student leaves the contents to cool. State what would you observe during the reaction. So what's happening is, iodine is purple in color. and H2 is a colorless gas. And when these guys are going to react, what are they going to form? H2 plus I2. It's a reversible reaction in which you form HI. And this is a exothermic reaction. The forward reaction is exothermic. So what's going to happen when you're going to cool it down? Exothermic. Forward reaction is exothermic. So when you're going to like cool it, I think the reaction should move forward, because when you cool exothermic reaction, it moves forward. So the reaction is going to move forward, and the purple color of this iodine is going to disappear, because you know that this fella is going to be purple in color, and the only observation we can write over here is about this thing, right? Because this is colorless, this is colorless. You cannot observe them, they're just like air. So you can only see this fella. So you write purple color disappears. I hope you understand what we're doing. Okay, chlorine and bromine can react to form NH3 to give N2N hydrogen halide X. We have some X2 stuff over here. X is going to be either chlorine or bromine, and we're making it react with ammonia to form nitrogen and 6 moles of HX. HX is going to be like HBr or HCl, whatever. The relative bond strengths of XX and HX determine the difference in the enthalpy change of the two reactions. Got it? What they're trying to say? And important stuff. That the bond energies, if it's going to be a chlorine-chlorine bond, it's going to be stronger. If it's going to be a bromine-bromine bond, it's going to be weaker. So the strength of these bonds basically determine your bond enthalpy and whatever. Okay, describe and explain the difference in the XX bond energies of chlorine and bromine. That's simple. Look, for chlorine, it's gonna be more. You know that a chlorine-chlorine bond is like this, and a bromine-bromine bond is like this. Over here, there's significant overlapping of the atomic orbitals, because look, if they're small in size, they can actually overlap each other very well. But if they're big in size, they overlap less because of the bigger atomic radius, and the bond length becomes longer, and the nucleus attracts the bonded pair of electrons less strongly. So that electrostatic attraction between the nucleus and the bonded electrons in a covalent bond is significantly reduced over here. Got it? That's the main point they're trying to tell us. That chlorine-chlorine bond, since it's shorter, since the chlorine atom has a smaller atomic size, that's the point. Since there's going to be like more overlapping of the orbitals, that's what we have to write. So Cl bond energy is greater than Br bond energy, because chlorine has a smaller atomic size. Hence, there is more significant overlapping of the orbitals. And Cl-Cl bond is stronger and shorter. Okay, that's my way of explaining things. You can use your own way. Describe the relative thermal stabilities of HCl and HBr. Okay, I just told you HCl is going to look something like this, whereas our HBr is going to look something like this. If I try to draw it in terms of atoms, this is your hydrogen atom. This is going to be your chlorine atom. But for HBr, this is your hydrogen atom. And this is going to be your bromine atom. So over here, you see that this bond is weaker than this bond. Why? Because look, Nucleus is here, nucleus is here. Over here, the distance of the nucleus from the bonding electrons is like a lot more. Over here, it's less. So this bond is going to be stronger. Hence, this fella is going to be more thermally stable than this thing. So if I'm going to heat it, if I provide heat, it's going to be easier to break this bond because it's already weaker, and it's going to be difficult to break this bond. So describe the relative thermal stabilities. Relative means there should be comparison between the two. So I'm simply going to tell the examiner HCl is thermally more stable. Thermally more stable than HBr. I don't need to explain my thing because it just says describe. It does not say describe and explain. But if they ask for the description, I've explained it to you guys. What's the thing that's going on over here? You have to look at the bond length, you have to look at the distance of the nucleus from the bonding electrons and all that stuff. Okay, define enthalpy change of formation. When they ever, there are keywords in the question. So over here, the keyword is define. Define means you have to simply learn the definition from the syllabus and then write it. So the definition for enthalpy change of, this is not anything conceptual. This is true, pure, God's honest truth it's learning. Okay? When 1 mole of a compound formation is formed from its element elements in their standard state under standard conditions. Okay, table 1.1 gives the relevant to the reaction of Cl2, okay, is relevant in NH3. I have the compounds this and this, and then I have the enthalpy change of formation this and this. Use table 1.1 to calculate the enthalpy change of the reaction of Cl2 with NH3. Achha, now there's a formula for enthalpy change of formation. If you have for the reactants and the products, then you can use a formula. But I know the formula, but still I do it with a Hess cycle. Why do I do it with a Hess cycle? Because the Hess cycle explains it all. So I'm going to go with the Hess cycle. You can use the formula if you guys want to. So I'm going to draw a Hess cycle in front of you guys to show you guys. So this is an element, chlorine. It's going to have, over here are going to be my elements in this below box. The delta node of formation of an element is 0. So over here it's 0. Then we have the formation of ammonia, 2 moles of ammonia. So 2 multiplied by negative 46. Then we have the formation of nitrogen. Element formation is 0. Then we have the formation of 6 moles of HX. HX is HCl, 6 moles of negative 92. Now we have to figure out the delta H node of reaction. We are going to make the cycles. The first cycle goes like they're going to start from here. So the first cycle goes like this, and my second cycle goes like this. So over here, both tails are starting here, both heads are ending here. Now in the first cycle, what is coming? This is coming in the first cycle, and these 2 arrows are coming in the second cycle. So the green cycle says 2 times negative 46 plus delta H node of reaction equals to the second cycle, which is 6 times negative 92. Equating the two and then solving gives me negative 460 kilojoules per mole. Simple equation solving I've done over here. Okay. I2 reacts with NH3 to form Ni3. Predict the shape of the molecule of Ni3. Explain your answer. So over here, I2 is reacting with NH3 to form Ni. What's going to be the shape of Ni? It's just going to be like NH3. So over here, I can see that you have nitrogen. That's going to make 3 covalent bonds with your iodine, just like it makes with your hydrogen in ammonia. And then there's going to be a lone pair sitting at the top, which is going to obviously cause repulsion over here. So when you have this kind of stuff, what kind of shape you have? Trigonal, bipyramidal. Why bipyramidal? Because it's like a pyramid at the base, and then there is this lone pair at the top. So it's like a pyramid, something like this. I don't know. I'm not good with drawing, but it's gonna be trigonal bipyramidal. Pyramidal, I don't know the spellings. Okay, the explanation is gonna be simple. 3 bonding pairs in 1 lone pair. 3 bond pairs in 1 lone pair. Simple. Got it? And the bond angle is gonna be 107. You guys should know. If there are 4 bond pairs, the angle is 109.5. And if there is 3 bond pairs in 1 lone pair, then you negative 2.5 from it to get your answer. And if there are 2 bond pairs, 2 lone pairs, then you negative again 2.5 from 107. So, okay, if you learn it, then you know it. Table 1.2 shows some information about the reactions of NaCl, NaBr, NaI. Okay, NaCl, NaBr, NaI, observation with Ag+. So you're going to have white precipitate for this, cream precipitate for bromide, and yellow precipitate for iodide. So over here I'm going to write cream precipitate because we have a bromide ion, and yellow precipitate because we have a iodide ion. And you should know that the precipitate of iodide and bromide are not very soluble in ammonia, but the white precipitates of chloride dissolve in aqueous ammonia. Type of reaction with concentrated H2SO4. You should know this reaction whenever halide salts react with H2SO4. That's an acid-base reaction. And then because sulfuric acid is a very strong oxidizing agent and the bromide and iodide ions are good reducing agents, over here redox reaction after that follows. What are the observations with concentrated H2SO4 of NaCl? So if you write the equation, you realize that NaCl plus H2SO4 gives you NaHSO4 plus HCl. Okay, so over here HCl is released as a gas. This is a solid, this is aqueous, no, not aqueous, liquid. Remember, no water over here. I don't think it's going to be aqueous, it's going to be liquid. NaCl solid. So where the HCl gas is going to give me some steamy fumes. HCl observation, I hope you guys know it's steamy fumes. NaBr, what's going to happen is that over here, acid-base reaction, you're going to form HBr. But after that, what's going to happen is that the redox reaction, you're going to form bromine gas, Br2. Okay, if you write the equation, let me write it. It's going to be NaBr plus H2SO4 giving you NaHSO4 plus HBr, and then this HBr is going to further react with your sulfuric acid to form SO2 plus Br2 plus water. And over here you remember that sulfuric acid is going from oxidation of +6 to +4, so you're going to have a 2 over here. Achha? So this bromine that's going to be formed as a result is going to be a brown, red, yellow liquid, whatever. So over here you write brown, red, liquid formed. That's going to be the bromine that's formed. And for over here, I hope you guys know that the black solid is going to be formed. That's going to be iodine. Yellow solid that's going to be formed is going to be a sulfur. Effervescence is going to be of the SO2 gas that's going to be formed. And then there's H2S gas that's also formed that has a rotten egg smell. All that stuff, I guess you should know. Okay. Suggest the identity of the species that produces each observation in the reaction of Ni with concentrated H2SO4. I just told you right now. Examiners thinking like me. Black solid was iodine, yellow solid was your sulfur, and the gas was your hydrogen sulfide gas, H2S. Iodine, sulfur, H2S. If you want the equations, the full equations, you should learn them. Iodine is going to be formed in all 3 equations in one equation you're going to form SO2, in the other you're going to form sulfur, in the third one you're going to form H2S. Table 1.3 gives some information about MgCl2 and SiCl4. Electrical conductivity when liquid, MgCl2 is going to conduct, our SiCl4 is not going to conduct. Observation when added to water, this thing dissolves and there's a vigorous reaction. You know this stuff, right? MgCl2 is an ionic compound, SiCl4 is a simple molecular compound, and the difference is that this is going to hydrolyze in water, this stuff is not gonna, it's going to dissolve. We know it, so no need to worry. Okay, explain the difference between the electrical conductivity of liquid MgCl2 and of liquid SiCl4. Refer to the bonding and relevant particles in your answer. Firstly, you know that when we have liquid MgCl2, it's going to be an ionic compound, so it's going to conduct. Explain the difference. We know it conducts. We tell the examiner MgCl2 is a giant ionic structure. In molten state, the ions are free to move. The ions are mobile and free to move through the liquid to conduct electricity. Second thing, why doesn't SiCl4 not conduct in liquid? You just know the structure, you know the bonding. There are two particles in your entire chemistry, AS level, O levels, IGCSE. There are two particles that can conduct. Either you have free delocalized ions, either you have free delocalized electrons. Not ions and electrons. Free delocalized ions or electrons can only conduct electricity. Only free delocalized ions and electrons. You just have to remember this stuff. So over here, if something is conducting, either it has ions or electrons. We just figure out that MgCl2 has free mobile delocalized ions. Now SiCl4, what does SiCl4 has or not has? Not conduct. It's because, look at the structure of SiCl4. You have one silicon that is covalently bonded to 4 chlorines. That's going to be a tetrahedral structure, right? Chlorine, chlorine. There is going to be this wedge shape, and then there's going to be a chlorine, and then you have this thing, and there is a chlorine. So this is your SiCl4, one molecule. Now if I show you the forces of attraction between the two molecules of SiCl4, there are weak intermolecular forces between both. There are no delocalized electrons. All the electrons of Si that are in the valence shell are involved in bonding. Got it? So we tell the examiner that SiCl4 is a simple molecular structure with covalent bonds. Because he's not asking about the structure, he's asking about the bonding with covalent bonds between silicon and chlorine. I'm gonna write everything. I'm a dash nerd who writes everything, and I want you guys to be nerds who write everything. Like, if you know the stuff that it's between silicon and chlorine, tell the examiner. Show the examiner that you are damn curious, you are damn interested in writing stuff. Examiner, tell the examiner. People say write to the point, write one line. I say write a lot. You need to show the examiner that I am interested. I am not taking it off. I'm not just like acting. I am genuinely interested in writing. And I know the stuff. Like, don't write incorrect stuff and write more. But if you know the correct stuff, even if it just takes a little more line and it takes a little more time, you have the time, do write it. Bonds between silicon and chlorine atoms. So it has no free delocalized, I'm gonna write everything, mobile electrons or ions to conduct electricity. Okay, suggest the pH of the solutions that form when each of the chloride is added to water. You know, MgCl2 is going to dissolve. And if you guys have learned this equation, that when you add MgCl, you don't need to even learn it. It just ionizes into Mg aqueous ions plus chloride aqueous ions, and what do we form? We form a neutral solution that has a pH of 6.5. So I've learned it 6.5 in the book. So you can write 6.5, but in the marking scheme it's 7. I think the examiner is kind enough that if you write 6.5, he should give you the marks, but well, I can't just like say anything, but I wish that he accepts it. But in the book, in the Cambridge book, it's written 6.5. Okay? Now SiCl4, but in the marking scheme I'm telling you it's written 7. But we know it's going to be neutral. Anyways, why it's going to be neutral? Because you're not forming any hydrogen ions. You know what changes the pH? Either it's OH negative or it's hydrogen. These change the pH. Okay, SiCl4. SiCl4 is gonna form HCl in water. Do you remember the hydrolysis of SiCl4? SiCl4 plus H2O, what do we form? We form SiO2 plus HCl. And how many moles of HCl do we form? We form 4 moles of HCl. And we're forming an acid over here when we add SiCl4 to water. An acid is going to do what? Make the pH drop away from 7. So either it's going to be 2 or 3. You can write anything. So I'm writing 2 over here. But in the marking scheme, it has a range. It has a range from 0 to 4. And you know why it's 0 to 4? Because we are forming some beautiful hydrogen ions. Aluminum oxide, Al2O3, and phosphorus oxide, P4O10. Okay, this stuff and this stuff are both used as reagents and catalysts. The melting point of Al2O3 is this, and the melting point of P4O10 is this. Explain the difference in the melting point of the two compounds. Lovely question. Okay, so over here you can see aluminum is what when you look at someone, what do you judge first? By the appearance of the thing, you judge about their family, which group do they belong to, which family do they belong to, what are their like references, how much wealthy they are. You judge stuff, right? You judge stuff when you see a person. When you see an element, a compound, you have to judge the elements over here. Which group does this fella belong to? Which group does this fella belong to? Right? So this belongs to group 3. Group 3 means it loses 3 electrons. And oxygen is a very, very violent element. It's very electronegative. It takes away electrons. So O2 negative means it belongs to group 6. It gains 2 electrons. Aluminum is curious, is like mad to lose electrons, and oxygen wants to gain electrons. One wants to lose, other wants to gain. What kind of bond are we going to form? We're going to form a ionic bond. Okay. The melting point of P4O10 is 340. We don't care. We just care about that P4. What is P4? Non-metal. Tends to gain electrons. What is oxygen? Non-metal. Tends to gains electron. This is phosphorus is in group 5. Oxygen is in group 6. Non-metal both wants to gain electrons. But no one's going to lose. So what's going to happen? You're going to form which kind of bonds here? You're going to form covalent bonds. Good, ho gaya. Explain the difference in the melting points of the two compounds. The difference is going to be simple, that Al2O3 is a giant ionic structure with strong electrostatic force of attraction. This is how, I've not seen the marking scheme, this is how I compose my answer. Structure with strong electrostatic forces of attraction between oppositely charged ions. Got it? Between oppositely charged ions. And then P4O10 is a simple molecular structure with weak intermolecular forces of attraction. Since they're weak, it's gonna require less energy. And then you have to make a comparison. The comparison is that ionic bonds are gonna be stronger than the intermolecular forces. First you tell about this stuff, and then the important line comes here that ionic bonds are stronger than your intermolecular forces. Okay. A 5 dm cube sealed flask, a 5 dm cube sealed flask contains 0.4 mole of carbon monoxide and 0.8 mole of H2 and Al2O3 catalyst. Carbon monoxide, hydrogen, and then you form ethanol. Methanol, it's methanol. I was just testing you guys. If you guys fell for my trap, that means your preparation is very good, mashallah. Okay, the equilibrium constant Kc for equation 1 is shown. This is the equilibrium constant. State the unit of Kc. Over here, what's gonna happen is that we have all gases. Good. So over here, we have to figure out the units for equilibrium constant, which is Kc. Kc is basically the concentration of your reactants and the products, right? Above you have your products and below you have your reactants. So for above, it's going to be mole per dm cube. Below, it's also going to be mole per dm cube. Brackets for carbon monoxide, then mole per dm cube, brackets square for hydrogen, because there's a square here. You cut this with this. What do you do then? 1 upon mole per dm cube squared. This mole per dm cube thing is going to come up. It's going to become mole negative 2 dm cube 6. How did this happen? We opened it, it became mole square dm cube negative 6, and then when it came up, it became mole negative 2. Below it was just 2. You know, when we bring things up, they get the negative sign, and below it was just negative 6, but when we brought it up, it became negative 6. Positive 6, I mean. So it's mole negative 2 dm cube 6. The equilibrium mixture contains 0.280 mole of your methanol. Calculate the value of Kc, give your answer to 3 significant figures. No worries at all. We have the equilibrium mixture contains these many moles. We always are going to take the volume moles divided by the volume, which is concentration. A sealed flask contains this much of carbon monoxide, this much of hydrogen. We have to make an ice table. What's an ice table? Ice table says that you write the equation carbon monoxide plus 2H2 gives CH3OH, and then you write your initial moles, you write your change in moles, and then you write your equilibrium moles. So the initial moles of carbon monoxide are 0.400. The initial moles of hydrogen are 0.800. The flask is heated to a temperature of 290, allowed to reach the equilibrium moles of your CH3OH is 0.280. Okay? Now look, initial moles were 0. But at equilibrium, you are having 0.280 moles. That means you form 0.280 new moles. Now you need to understand that the ratio between this is 1 and 1. So if you're forming 0.280 moles here, that means you are using 0.280 moles of your carbon monoxide, and the ratio of carbon monoxide to hydrogen is 1:2. So that means if you are using your 1 mole here, this much, you're gonna double it for hydrogen. So 0.280 ka double is gonna be 0.280 times 2, 0.56. 0.560. And now, you have carbon monoxide, you have hydrogen, and you have methanol. What do you do now? You know their equilibrium moles. You subtract initial moles from the used moles. So 0.400 minus 0.280, 0.56 minus 0.24. So over here I have 0.240, then 0.400, 0.40 minus 0.280, 0.280. By the way, if you guys don't understand anything, just like feel free to ask. You have the moles of everything at equilibrium. What do you do? What do you do to find out the concentration? What do? You divide the moles by the volume. Then what do you get? You get the concentration. Volume is 5 tm cube. We have to divide these moles by 5, divided by 5, divided by 5, divided by 5. Now what do we have? We're going to get the concentration. So now I have the concentration of all. And after that, what do? Divided by 5, just plug it in the calculator like this if you guys are comfortable, but I'm not, so I'm going to divide it. 0.12 divided by 5, 0.024, 0.024, 0.24 divided by 5, 0.24 divided by 5, 0.0480, 0.0480, 0.280 divided by 5, 0.280 divided by 5, and that gives me 0.056, 0.056. Good. Now what do you do? What do you do, guys? You take these things and put them in your Kc expression. For methanol, it's 0.056. So 0.056 brackets. Then for hydrogen, it's a square. And for carbon monoxide, it's simple. So carbon monoxide is 0.024. Multiplied by the for that of hydrogen, that is 0.0480 squared. You plug this entire value in your calculator, and what do you get? You get 1.01 into 10 raised to power 3. And now what? Guess what? You have to write this over here. But if you write this like this, you're not going to get your full marks. What do you have to do? You just found out the unit. Mole negative 2 dm6. You have to write this over here. Mole negative 2 dm cube 6. Done and dusted. State and explain the effect, if any, on the value of Kc when the overall pressure in the seal flask is increased. No effect. You know why no effect? Because Kc is only affected by temperature. The only thing, just note it down somewhere, the only thing that can affect Kc and Kp is your temperature, your pressure, your concentration. Nothing affects it. No effect. Kc is not affected by pressure. No effect, because Kc is not affected by pressure. Okay. P4O10 catalyzes the reversible reaction of carbon monoxide with H2 to form CH3OH. You have carbon monoxide, you have 2H2, you have CH3OH. P4O10 then acts as a dehydrating agent, causing CH3OH to form this. Okay, a lot of stuff happening, but we don't care. We're going to just break it down anyway. This stuff is a catalyst, so not going to be used in the reaction, so don't get confused by it. carbon monoxide and hydrogen. It formed our methanol. Methanol is an alcohol. Okay, now alcohol is being dehydrated, and when we dehydrate alcohol, we form this. Explain how the presence of a catalyst affects a chemical reaction. Simple, simple. It decreases the activation energy. You remember, I hope you guys remember. Initially, our activation energy used to be something like this. Like if that's because this is an endothermic, the activation energy is going to be this. But when we add catalyst, it becomes this. So from this green line, activation energy decreases to this black line. Okay, so over here, what we're gonna write? Okay, what are we gonna write? Which color should we choose? Catalyst decreases the activation energy by providing an alternative pathway for the reaction mechanism to proceed. I'm gonna write all. Providing an alternative pathway for the reaction mechanism to proceed. Okay, construct an equation for the dehydration reaction of your methanol to form this. Good, okay. Please draw the structures, otherwise I don't think, like, you might not be able to do it, or there might be some problems. So let's draw the equation, draw the structure so we understand what's happening. H, OH. Then you're adding construction equation for the dehydration. What's being added? P4O10 catalyzes. P4 then acts as a dehydrating agent. Okay, so P4O10 is going to act as a dehydrating agent, and we are going to form CHHH, OCHHH. Can you see one thing over here? The carbon length is increasing. So that means I need to use 2 moles of this thing because I need 2 carbons there. And if I have 2 moles of this, HCHHOH, if I have 2 moles of it, I have only one. I need this entire thing is going to be removed because over there I only have this part. I don't need an OH and H. So I'm going to form +1 water over here. So that's simple. 2 moles of CH3OH is going to give me this CH3OCH3 thing plus 1 mole of water. Do you get it? See it. I've drawn it for you. Look what's happening. 1 mole of this, 1 mole of this. Forming this stuff. Plus we're removing a water molecule. Only then it's possible to form this. Otherwise it's not going to form. See it. It's not going to form. Write an equation to show the reaction of P4O10 with an excess of water. P4O10 with an excess of water. So if we're going to add P4O10 to water, what are we going to form? We are going to form our phosphoric acid, H3PO4, 4 moles of it. Are we balanced? 10 oxygens here, 4 times 16 oxygens here, 3 times 12. So we add a 6 here. 6 here. Are we balanced? Yes, we're balanced. We're good to go. Simple, you have to learn it. Okay, so now we move on to organic chemistry. Propane-2-ol, okay, CH3,2CHOH is sometimes added to fuel to help it burn. That means propane-2-ol must have a very good flammability or combustibility or whatever. It's good for burning things. This is the formula. We added to fuel. Figure 3.1 shows some reactions of propane-2-ol. So we have propane-2-ol. That's the skeletal formula. Over here, reaction 1, we've added acidified K2Cr2O7. What happens when we add, what is this? What is acidified K2Cr2O7? It is a oxidizing agent. And what happens when we add oxidizing agents to an alcohol? Can an alcohol oxidize? Especially a secondary alcohol? What substance does it oxidize to? Do you guys remember anything? Secondary alcohols oxidize to form ketones. So over here, we're going to form a ketone. And what kind of ketone? Let's do it and see it for ourselves. So propan-2-ol is going to look something like COH, H, CH3 and CH3. Good? Over here, now what's going to happen is that just for your convenience, so that it's easy for you, I'm going to move this thing here and this thing here. Good ho gaya? Now see, when I oxidize something, oxidation is loss of hydrogens. So I'm going to take out one hydrogen from it. I'm going to take out second hydrogen from it. And I'm adding 2 oxygens to it. Okay, 2 oxygens. 1 oxygen I'm going to add to the hydrogens I've taken out. No, 1 oxygen will do my work. I don't need to add 2 oxygens. So let me just add 1. 1 oxygen can do my work. I'm just going to add 1 oxygen to the water that I have brought out. And this bond is going to be removed. And I'm going to form a double bond here. Good? Good to go? So, what am I forming? I'm forming propanone, which is a ketone. What did I do? What did I do to make it? I had 2 hydrogens, one here and one with the OH. I took out the 2 hydrogens, joined them with an oxygen, formed water, 1 mole of water. And secondly, I just formed a carbon-oxygen double bond, which made it a ketone. Okay, now we have propan-2-ol and we're making it react with concentrated H2SO4. What is H2SO4? What kind of reaction is happening over here? It is a dehydrating agent. So what we're doing? We are basically dehydrating our alcohol. And when we dehydrate alcohols, what do? Let me again make our propan-2-ol. Propan-2-ol is going to be like COH, CH, H. I'm making the full diagram to help you guys realize what kind of stuff is happening over here. Now, what do? I take out OH from one carbon and H from another carbon. I take out a water molecule because I have added a dehydrating agent. H2SO4 is a dehydrating agent. So what I'm going to do, it's going to dehydrate. Hydrate means to add water. Dehydrate means to take out water. So I'm going to take out an OH and H from here. This is what I've taken out. These bonds are going to be removed and I'm going to form a carbon-carbon double bond. And what kind of substance do I form after dehydrating my alcohol? I form propene, which is a alkene. You can see the skeletal formula of propene over here. Got it? And what do I form? I form a water molecule. Okay. Reaction 2 involves alkaline iodine. What am I doing here? Iodoform. You guys remember? I'm forming iodoform and I'm forming a ion. A carboxylate kind of carboxylic acid kind of ion. Alkaline I2. So over here, for instance, if I added NaOH, then I can form CO2Na, a salt of the acid, the carboxylic acid that's going to form. So that's going to be ethanoetine. This is triiodomethane. Whatever you call it, CHI3, triiodomethane. And this substance is yellow in color. And how did it form? Because I had a secondary alcohol. Secondary alcohol have this group. Where is this group? Let me draw it and then show it to you guys. This thing. CH3CHOH. This thing gives you a yellow precipitate. Okay, so this group is going to give you a yellow precipitate. And then if you're dealing with ketones or other substances, then this group, C double bond O, these kind of things just give you yellow precipitate. Just leave it. Okay, draw the structure of organic compound K. What is K? K is propanol. So draw the structure. So should we draw the skeletal formula? I think, because look, everything is given in the form of skeletal formula, but structural formula can also be written. But the question, look, they've given everything in skeletals. Here skeletal, so I think I should also draw skeletal over here. So 3 carbons, 1, 2 and 3. So, and double bond O on the second carbon. Done? State the observation you would make in reaction 2. Where is reaction 2? This is reaction 2. This is a iodoform test. So I'm going to observe a yellow precipitate. And that yellow precipitate I told you is of CHI3 fella. State of type of reaction that is shown is reaction 3. Okay, so over here in reaction 3, you can see that you are adding H2SO4. And you are removing a molecule. Whenever you remove a molecule from one molecule, that's called an elimination reaction. This might seem a bit like complicated, but there are types of reaction in organic chemistry, like addition reaction. The types are addition, then there is substitution, then there is elimination, then there is oxidation, then there is reduction. So these are the types of reaction you're going to come across in organic chemistry. So this one is an elimination. Why? Because we're eliminating a water molecule from an existing molecule. We're taking out a molecule. And if we were to add a water molecule to it, when we hydrate alkenes using phosphoric acid and whatnot, 300 degrees Celsius, 60 atm pressure, whatever that thing is, that's called addition, because we add something. But over here, we're taking out something. So this is an example of elimination reaction. Complete figure 3.2 to show the pi bond in L that is formed from orbital overlap. Pi bond. Okay, so these are sigma bonds. Single, 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 single. Over here you can see carbon is not fully saturated, because carbon makes 4 bonds. There are 1, 2, 3. The 4th bond we have to show. Up now, what is the most common mistake over here? People are gonna draw a line. They've already drawn lines to show you guys the single bonds. We have to show a pi bond. And how do we show pi bonds? We show pi bonds by making an electron cloud, a bean-shaped cloud, above and below this nuclear thing. Because what's happening is that the overlap of orbitals is something like this. This is the overlap area. So we show the overlap above and below the nuclear axis. There's no heads-on overlap. It's a sideways overlap. Okay, so next. Propan-2-ol reacts with sodium to produce some kind of anions. Okay, so we are making an alcohol react with sodium. What is going to happen? Aren't we going to produce hydrogen gas? Do you remember that reaction? Alcohol plus metal gives us hydrogen plus ethoxide, methoxide, or whatever, those kind of ions. Write an equation for the reaction of propan-2-ol with sodium. No worries, dear, no worries. Okay, propan-2-ol. First, let's just do it ourselves, and then we're going to write the equation. So propan-2-ol, carbon, OH, CH, H, 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 CH, H, H. I know, it's not very good. Plus sodium. Now what's going to happen is that this sodium is simply gonna come in place of this hydrogen. And this hydrogen is gonna form hydrogen gas, like half mole of hydrogen gas. And we're gonna form this compound. Got it? Simple. So, write an equation for propanol. What is the formula for propanol? Just write C3H7OH plus sodium is gonna give me C3H7 C3H7O negative Na positive plus half moles of hydrogen. Next part says that the reaction of 2-bromopropane with this thing, anions, follow SN1 mechanism. Complete figure 3.4 to show this mechanism include charges, dipoles, lone pairs, electrons, curly arrows as appropriate. Okay, so we have to draw the SN1 mechanism. First things first, this carbon-bromine bond should break. That's how we are gonna add this stuff to this thing, right? We have to add this stuff to this thing. So for that, first carbon is going to be partial positive, bromine is going to be partial negative, because bromine is more electronegative. It's going to pull carbon's electrons towards itself. So you know now what's going to happen here. Good. H3, once this happens, is bromine is going to take away carbon's electrons, and now we have H3 CH3, and this fella is gonna be positive. So this thing is gonna attack this fella, and once it attacks this fella, what is gonna happen? Once it attacks it, we are gonna form this compound. Are we done? Curly arrow from the lone pair to this, then we have to show this intermediate and we have to show the correct dipoles, and we are awarded with the 3 marks. So 1 mark was for the attack, 1 mark was for the intermediate, and 1 mark was for this thing. So done. Easy. What's difficult? Suggest how the rate of SN1 reaction would change if all the 2-chloropropane were used instead of 2-bromopropane. The rate would decrease or increase. What do you think? What should happen? Carbon-chlorine bond and carbon-bromine bond. What's stronger? Carbon-chlorine is stronger, na? So if this is stronger, instead of bromine, if we had chlorine here, the bond wouldn't break easily. And if the bond wouldn't break easily, the rate would decrease, because the rate is dependent upon this bond breaking. The faster it breaks, because this is always ready to attack this thing. So what matters is that when will this bond break, right? Suggest how the rate of SN1 reaction would change if all the 2-chloropropane were used instead of 2-bromopropane. We write rate decreases because carbon-fluorine bond is stronger than carbon-bromine bond. So more energy required to break it. Okay. N is also added to petrol. Okay, so now we are adding N to petrol to make it burn more smoothly. Construct the equation for the complete combustion of N, C6H14O. Good. So plus oxygen, we have to make carbon dioxide and water. And how many moles of carbon dioxide are we going to make? 6 moles. And then for water, we're going to make 7 moles. 6 2 times 12 plus 7, 12. I'm very bad at maths. Look what I'm going to do now. 12, 13, 14, 15, 16, 17, 18, 19. So I have 19. 1 oxygen is here. That means remaining 18 oxygen. So 9 moles here. Done. Compounds P and Q are structural isomers, define structural isomer. Same molecular formula, different structural formula. Am I correct? Yes, I'm correct. Same molecular formula, different structural formula. P shows geometrical isomerism. Draw the geometrical isomer of P and explain why the two isomers are not identical. Draw the geometrical isomer of P. Explain why the two isomers are not identical. Okay, geometric means cistrons. So basically over here, where is P? This is P. You can see that it has carbon, carbon, CH3 above, and then there is one C2H5, this entire thing, two things above, one hydrogen below and one hydrogen below. So now I have to just flip it. So what I'm gonna do, double bond in the center, this is gonna be below and this thing is gonna be above. So that's the way I make it. Done. Now look, this is below, this hydrogen is above. So this is basically trans. Okay. Why do we form geometric isomerism? Over here the question is this. Why do geometrical isomers form? They form because there is restricted rotation around the carbon double bond. This group that is above cannot come below and this group that's below cannot come above. It's gonna remain like this. Over here, both groups are above, they're gonna remain above. So the problem because of which they are too different, despite having same molecular formula, same structures, they're still different arrangement because they're like geometric isomers, so they're part of the stereoisomer thing. So different arrangement of atoms in space is what they have. Why do they have this? They have this because of restricted rotation around the carbon-carbon double bond. So as we know that alkenes can only react with aqueous bromine because of one mechanism. And what is that one mechanism? It is electrophilic addition. So bromine reacts with alkenes because of electrophilic addition. Basically what happens is that dipoles are induced. This becomes partial positive, this becomes partial negative. What happens is that this pi bond has lone pairs, not lone pairs, it basically has pi electrons over here. These pi electrons are very like out of control of the nucleus, so they attack this partial positive bromine. This bond breaks heterolytically, the down bromine gets the electrons, and then that's how electrophile is being added. Q is oxidized. Q is oxidized by acidified KMnO4 forming two different organic products. Okay, so where is Q? This is Q and we are oxidizing it by using KMnO4. There's an alkene functional group over here, and remember that we have hot concentrated, so there's going to be a cleavage and the bond is going to break, forming two different organic products. Construct an equation for the reaction. Use O to represent atom from oxygen from the oxidizing agent. Asha, by the way, you got to know one thing, that this is a carbon, this is a carbon, and this bond is going to break here. This carbon is attached to two other carbons. This carbon is only attached to one other carbon and one hydrogen. So this carbon is going to form what? This carbon is going to form what? It's going to form a ketone. So over here, this carbon is going to form propanol, which is going to look something like this. CH3, CH3, and this carbon right here, it's gonna form our carboxylic acid, our ethanoic acid. Why? Because this is attached to one C and one H. When you have one methyl group attached, you form, or ethyl or propyl or whatever, one alkyl group, then you form your acid. So we are going to form carboxylic acid. Done? Now you see for yourself how many oxygens are we adding to this thing. One oxygen is what I am adding over here. One oxygen I'm adding here. One oxygen I'm adding here. So I'm adding 3 oxygens in total to this thing to form my acid and my ketone. So over here I'm gonna write plus 3 oxygens, and then I'm going to form my carboxylic acid, which is going to be CH3COOH, and then I'm going to form my ketone, which is CH3COCH3. Done and dusted. Next. Okay, Q reacts with HBr to produce two structural isomers, R and S, as shown in figure 4.2. Q. So this is my Q. It has this double bond, and then it reacts with HBr, which is hydrogen bromide. There's going to be an H here and a Br here. This is going to be partial positive. This is going to be partial negative. This lone pair is going to attack this. And when it attacks it, what's going to happen is that then you're going to form a carbocation, and then this stuff is going to happen. So one possibility is that you form a secondary carbocation, and the second possibility is that you form a tertiary carbocation. Because look, if you try to open the structure, this is basically C double bonded C, CH3, CH, and then this fellow over here is CH3 and CH3. If I bring this thing like this, CH3. Done? Okay. What do you do now? You just... What do you do now? You just need to add HBr. Now there are two possibilities, right? First is that bromine can get attached over here and H can get attached over here. Good. This one's a good one because the negative part is being attached to the carbon that is less hydrogen. So this is going to be the major product, which is represented by S. And the second possibility is that bromine basically gets attached to this carbon, and that's going to be a minor product, because over here the problem is that the negative part is being attached to the carbon that has less alkyl groups with it. We need more alkyl groups. Why more alkyl groups? Because we need positive inductive effect. Okay, state and explain why isomer S is the major product of the reaction. It is simple. In the formation of S, a tertiary carbocation intermediate is formed. Which has 3 alkyl groups attached to it. So there is more positive inductive effect. I'm a little bad with spellings. Positive inductive effect. Okay, the mass spectrum of R shows peaks at mass to charge ratio 150 and mass to charge ratio 152. So the mass spectrum of R, this is my R. I'm getting peaks at 150 and 152. Suggest the structures for the ions responsible for these peaks. Okay, so why do we make peaks in the spectrum? Basically, this is the M peak right here, and this is the M plus 2 peak. Do you understand anything? This is an M plus 2 peak, and this is an M plus peak. So we have to first check either it's a molecular ion peak. I think it should be molecular ion peak. So let's just write. So we have CH3, 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 1, 2, 3. Then we have CH, 1, 2, 3, 4, 5. So 5 into 12. 5 into 12 plus bromine. What's the mass of bromine? What do you think I should take? 83? No, by Smith. I'm so sorry. What am I doing? 35 or 79.9? What do you think should I take? I take 79.9 because that's the mass. Plus 79.9 plus we have how many hydrogens? 3 plus 3 plus 1 plus 3. 3 plus 3, 6. 6 plus 3, 9. 9 plus 1, 10. I'm so good at it. Plus 10. We form 149.9. That's almost 150. So 150 is the molecular ion peak, and 152 is the M plus 2 peak because of this bromine, because of this halogen, because you know there are not just one type of bromine. There are not just one type of bromine. There is bromine 79 and then there is bromine 81. So there are two isotopes of bromine that are causing this. So over here we have to draw the structures. We have to just draw the structure of the same thing like this. But over here we have to write bromine. This one is 79. And this entire is a ion. You know, ions cause peak, not a proper thing. Like, not the, what do you call them? Not the molecule is gonna cause peak, molecular ion. Like, you just knock off one electron from the entire molecule and you form a ion. Okay, second peak is gonna be because of the other isotope, that is bromine 81, and you form a positive. This was, by the way, difficult. If you guys don't know the infrared or mass spectrometry, this thing is difficult to judge the molecular ion peak. Okay, figure 4.3 shows the synthesis starting from T. A different isomer of R in S. So we have T, which seems like a halogenoalkane. What kind of? This is a carbon, 2 alkyl groups, 1 hydrogen. So this right here is a secondary halogenoalkane. Secondary halogenoalkane. And over here, it's basically this bromine is being substituted. This is a nucleophile. You know, bromine is a nucleophile. And over here, it's being substituted by the CN. CN is also a nucleophile. So one nucleophile substituting another nucleophile. So this is nucleophilic substitution happening. And for bromine, like the halogenoalkanes, how do we do nucleophilic substitution? Do you guys remember anything? We take alcoholic NaCN or alcoholic KCN and we heat it. So that's how we do it. Identify the reagent and condition for reaction 1. Alcoholic KCN and heat under reflux. Okay. Second is we are doing acidic hydrolysis of this nitrile part and we're forming a carboxylic acid. This is going to be the acid and this is going to be the side chain then. Reaction 2 is a hydrolysis. Construct an equation for reaction 2. Now they're asking equations for all the difficult reactions. So keep in mind, how do we do the hydrolysis? We take 2 waters. We take 1 HCl. You have to learn this. And whenever we are doing acidic hydrolysis, the first thing that we're going to form is we're going to form C2H5 2CHCOOH, and then we form ammonium chloride because we form ammonia gas. And then what happens is that this HCl is basically going to react with the ammonia gas that's going to be formed. That's the proper reaction. You don't have to learn, you just have to learn the equation. If you guys want to ratify the equation. It's going to form ammonium chloride. Okay. V reacts with propan-2-ol. V reacts with propan-2-ol in the presence of a catalytic amount of H2SO4 to form organic compound W. Good. We have V that's going to react with propan-2-ol in the presence of catalytic amount of H2SO4 to form organic compound W. Where is V? This is V. This is an acid which is ready to react with an alcohol in the presence of acid catalyst. What do we form? What do we form, kiddos? Acid plus alcohol. We're gonna form a ester plus water. Reaction of V with propan-2-ol, type of reaction condensation. Esterification is an example of condensation reaction. I hope that needs no clarifications. Functional group formed, ester bond is going to be formed. Molecular formula of organic product W. What do? We take propan-2-ol and this thing. C. Let's first draw it. CH, CH3. So the molecular formula of this thing is 1, 2, 3, 4, 5, 6. C 1, 2, 3, 4, 5, 6. H is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And O2. C6H12O2. Okay, so it's C6H12O2 plus my alcohol. Propan-2-ol is going to be C3H7OH. And over here, what I'm going to do is I'm going to remove one water out of it. So it's going to become 6, 7, 8, 9, C9H water. It's total 8 plus 12. 8 plus 12 minus 2. So it's 8 plus 12 minus 2. That's 18, C9H18 and O2. Because one O is going to go. I hope that makes sense. I just joined the two things. So it's C9 H18 O2. Well, child's play, very easy. You don't have to do anything. You just have to join this stuff and this stuff. That's all. Thank you. Bye bye.